Hello everyone. Today I'm very happy to share our latest work, Medusa attack exploring security hazards of in-app QR code scanning. It's a collaborated paper with Xing, Yuheng, Zhang, Zhang, Zeyuan, Chen, Wang, and Siqi, Yuheng, Elisa, Bertino, and Juanru. We discovered new security risks in QR code ecosystem and proposed a novel attack, Medusa attack, which can exploit vulnerable built-in QR code reader to remotely attack the mobile app. Okay, I'm sure that most of you have ever used or seen QR code before. As we can see in this picture, a QR code is a type of two-dimensional matrix barcode. It contains specific information like description, website, URL. This information can be read and passed by machine, but can be not easily distinguished by human. With the popularity of smartphones, QR codes are more and more widely used for convenience and efficiency. By 2022, more than 5.1 billion users had ever used and scanned the QR code. Today, there are two ways to use a QR code. One is a traditional way, using a static QR code, which only embeds static constant text information. And another one is more advanced and popular nowadays, which is dynamic QR code. It can not only redirect user to a new website, but also can be used as program input arguments to perform further complicated activity. To achieve such advanced features, an app built-in QR code reader is necessary. So what is a built-in QR code reader? As you can see in this slide, a built-in QR code reader is usually used to extract encoded data from external QR code and then execute relevant app function without any additional interaction with user to perceive a seamless user experience. It contains three main parts: a QR code scanner, a QR code parser, and a QR code executor. After scanning a QR code, the scanner will first decode the QR code, and then the parser will further handle the data and send it to the executor. After that, the executor will use this data to execute and invoke the different functions and finally complete the operation. Among these app functions, one of the most important ones and we are mostly focusing on is that the executor can create a web view object, which can be considered as an in-app web browser to open a certain URL and interact with the remote server. During this procedure, to facilitate interaction with those remote servers, many apps usually provide some local functions registered in the web view object. These functions can be remotely invoked by the remote server, so that we call them remotely accessible handler, RAH. Especially, the remote server can use this RAH to access local app services and resources, like accessing app credential, local file, or even GPS service. And then the RAH will return the certain resources and their execution results to the remote server. So here is the problem. As it's impossible for a user to distinguish a malicious QR code, we consider the built-in QR code reader, especially the QR code executor, should be equipped with enough security checks for the input data from external QR code. Otherwise, with a malicious QR code, an app will be likely to be tricked into opening a malicious website and then executing an unexpected function. For example, if the original function is to log into user's account, but the app can be unexpectedly exploited to send the user credential to an attacker server without user permit. And unfortunately, existing works are mostly focusing on the QR code scanner and QR code parser instead of the activities after QR code scanning, that is hijacking mobile apps while RH invoking. So in this work, we first propose a new attack, Medusa attack, to exploit such vulnerable built-in QR code reader. During this attack, an attacker will trick the user into scanning a carefully constructed QR code. Then the extract data containing the tampered function parameters will be used by QR code executor, and finally invoking unexpected function to perform sensitive actions. And we consider the root cause of the Medusa attack is the QR code executor lacks enough security checks for the extract data from external QR code, and there is no security verification regulations in existing QR code standard. So in order to detect whether an app is vulnerable to our Medusa attack, we also propose a three-step analysis framework. With the first two steps, we can determine if an app is vulnerable to Medusa attack, and in the second step, in the third step, we launch POC exploits to confirm the result and evaluate the efficiency of our attack in real world. Let's start with the first step. Before we can launch the attack, we need to identify which custom RH can be utilized. And so the first step is to detect custom RH. Here we don't consider the standard RH because they are usually open sourced, as everyone will be able to check and audit their code implementation. But on the contrary, custom RH are usually developed by various vendors, and their implementation code is a little bit different and not publicly available. So in this work, we only focusing on such custom RH, and we combine both static and dynamic analysis to identify them. We first utilize RH signatures and relevant method information to pinpoint all possible RH, and then we conduct dynamic testing to check if one RH can be invoked by QR code scanning function. Because only one RH can be invoked by QR code, an attacker can then exploit vulnerable built-in QR code reader to launch our attack. After confirming that, in the second step, we detect if any insecure QR code reader exists. To achieve that, we collect and construct three types of QR code, including official QR code encoded with official URL, and QR code encoded malicious URL. And then we test if this QR code can be accepted or allowed by the built-in QR code reader. And based on different input, we also classify different vulnerability severity. We consider a QR code reader is insecure as long as any third-party URL accesses are allowed. In this way, an attacker can construct malicious third-party website contained in the malicious QR code, which will be accepted by the QR code reader, and then the remote server will be able to invoke the local RH and access the app-native resources or functions. And after the two steps, we can determine if an app is vulnerable to the Medusa attack. And in order to verify the result and attack efficiency in real world, in the third step, we launch proof of concept Medusa attack exploits. With the information obtained from the first two steps, we can then try to construct malicious QR code to invoke sensitive RH. If any native sensitive services are triggered or resources are accessed, the vulnerable can be confirmed. To evaluate Medusa attack in real world, we conduct experiments on 4 data sets, including 800 popular apps from 3 mainstream Android and iOS app stores, which involved 2 largest ecosystems, that is United States and China. Before that, to confirm the usage of built-in QR code in an app, we manually checked whether it supports QR code scanning function. And if so, we then can apply our detection method into it. The results show that nearly half of the 800 apps utilize built-in QR code reader, and they are used for more complicated tasks such as payment, online meeting, and login. And after that, we launched our detection process. In the first step, we found custom RAHs are present in 605 mobile apps. And even for the iOS US dataset with the lowest ratio of RAH, more than half of the apps in the dataset use at least one custom RAH. And among those apps, we found 123 of them are having secure built-in QR code reader, and 115 apps don't apply any sanitizer for the input data extract from external QR code. We finally launched the real-world exploits on the vulnerable apps. In order to access critical services, we manually checked those RAH interface name and labeled 515 custom RAH as sensitive ones. And we found 317 of them returned their execution results to the remote server, which can be abused to conduct high-severity security or privacy attack. And a total of 46 apps are vulnerable to Medusa attack and can be exploited in real world. So in conclusion, in this work, we systematically analyze the security of modern QR code scanning function and propose a new attack, the Medusa attack. And we also propose a three-step detection approach to identify risky implementation among various built-in QR code reader. And with an evaluation of 800 popular Android and iOS apps, we found some of them were vulnerable to Medusa attack, and 46 apps contained critical or high-severity vulnerabilities. We have reported this result to relevant vendor and helped them fix the issues. And last but not least, please do not scan any unknown QR code. And if you can get more details on our website, and if you have any question, I'm very happy to answer it, and you are also welcome to contact the corresponding authors if you are interested in our project. Thank you very much.